Hi, my name is Daniel Sejer Petersen, and I'm an associate professor in medicinal chemistry at the University of Copenhagen in Denmark. I'm here today to give you a short introduction to dry column vacuum chromatography, or DCVC for short. Now, this is a very basic tutorial. I'm only going to show you very basic equipment you need and how to set up a column and run it. So no fancy experimental details today or expert tips and tricks. If you're interested in further details, at the end of this introduction, there will be links to useful websites and to publications where DCVC experts have lots of useful information for you. Right, so what is DCVC? Well, DCVC is basically a silica-based column chromatography technique that complements flash column chromatography. So the big question right now for you, of course, is why should you start using DCVC instead of flash column chromatography? Well, there are many advantages over flash column chromatography when we think about DCVC. Two minor advantages, but interesting and positive ones, is that it's a vacuum-driven technique. It's much nicer to work with vacuum than with pressure in an synthetic organic lab. Secondly, the basic equipment you need for DCVC is available in all well-equipped labs. You don't have to have the glass blower make anything special for you. So you can just get going from immediately if you want to. Now, for the real advantages, first off, it's a huge resource saver, right? So you need a lot less silica for DCVC and much less solvent that you would use for flash column chromatography. Another real advantage is it's a very fast technique, so in a matter of hours you are completely done with DCVC, whereas flash column chromatography can drag on for hours and hours. Finally, I guess the biggest advantage of DCVC is in fact that you can scale it up very easily and do hundreds of grams of purification. So personally, I've done a 200-gram purification on several occasions, and this is completely unthinkable in a standard lab if you're using flash column chromatography. Advantages or disadvantages of DCVC. So when would I use flash instead of DCVC? For really small scale stuff, I think it's superior. So if you're working with 50 milligrams or less, I think DCVC is tedious. Flash column chromatography much faster and easier to do. And secondly, a very important detail is that if you have volatile compounds, DCVC is not good because it's a vacuum-driven technique. So definitely do flash for volatile compounds. Furthermore, low boiling solvents are problematic for DCVC. It can be done, but it requires a bit of experience. So dichloromethane, acetone, and ether, for instance, that are very popular for flash column chromatography are a bit harder to implement for DCVC. So that's the basic pros and cons and background for DCVC. And now we're ready to have a look at the equipment you need to run a DCVC purification. So let's have a look at the equipment you will need to run a DCVC separation. So first, let's have a look at the columns. The column is simply a sintered glass funnel that most labs will have on the shelf. Unlike a standard sintered glass funnel, this one has to be a little bit taller. So ideally, you will have a column that looks something like this. So it has to be around 7 to 10 centimeters tall. It has to accommodate a silica column that's about 5 centimeters tall, and there has to be headspace for loading a compound and for loading the solvent while you're running the column. These can be purchased or custom made in various diameters, and so depending on how much compound you're purifying, of course, the diameter of the column has to go up. The most commonly employed ones are the 4 and 6 centimeter diameter columns. These are really good for most applications, ranging from 100 milligrams to, I would say, up to 10 grams, depending on how hard the separation is, of course. Okay, so now we have the column in place. When we pack the column, the silica has to be very firm. So you need to have some good presses and spatulas to compact the silica. Now, I will shortly show you how to actually pack the column, but let's first have a look at the equipment you'll need. And of course, you can do countless variations on this theme. What we use here at the University of Copenhagen is these plastic rods, presses. They look like this. And they are really, really practical when you are packing your silica. You can, of course, have custom-made fancy stuff that looks like that, for instance. That's up to you, of course, how much you want to invest in it. One more thing that you require, and this is very simple to make yourself, is a spatula that has a bent tip. This is for compacting the edges of your column. And these are also available in all kinds of sizes, of course. You just have to buy the right size spatula. This is something that our workshop does. We buy the straight spatulas and they bend the tip for us. Okay, so now we have the column and the packing gear in place. Now we have to look at the receiver to put your column in after you've packed it. This is the most basic setup you can imagine. So we already have the column in place. All you need is a separatory funnel like this, so just a standard SEP funnel, nothing fancy. Then you need some type of vacuum adapter, and these are normally made of glass. Here at our department, we use these made of Teflon. So it's basically a vacuum adapter with a sidearm, right? Just plunk that in there. Next, you need a three-way tap. This is essential because you want to be able to release the vacuum while you're running the column, so you can get your fractions out at atmospheric pressure. And that's simply attached here. Like that. And that's your basic assembly. Now you just need to pack your column, put it on top, and you're ready to go. That was the basic setup. There are nicer ways to do this. And the preferred setup that we have in our lab looks like this. So we have these receivers made by the glass blower. And it's essentially a SEP funnel, but now the vacuum adapter is integrated into the glassware. So it's just nice and convenient to work with, and it has a good size. And of course, we have these made even bigger if we're doing very large-scale separations. We prefer to not have ground glass joints for these, but of course, that's an option. It's up to you what you would like to work with. But we prefer this, and we simply have these rubber bungs we put in. And like before, we simply put our column on top, and we are ready to go. Again, essential with the three-way tap, otherwise you will lose a lot of time because you'll have to turn off the vacuum all the time. So always have a three-way tap on. Right. Again, you can see here I'm using the plastic one. Obviously, you can use a glass three-way tap. It doesn't make any difference. We like these because they don't break when we drop them on the floor. Okay, let's have a look at a sophisticated solution, an advanced solution. So one of my colleagues has been kind enough to borrow me his personal DCVC equipment, and it looks like this. And this is a different way of doing it, where he actually has the vacuum attached to the sintered funnel, and he has a ground glass joint. And now he's actually collecting fractions in Erlenmeyer flasks. So he has a lot of these standing in the hood, and he simply collects a fraction, and then he moves to the next Erlenmeyer flask, collects another fraction, and he moves along like that. So that's another option. There's countless ways of doing this. You just have to find the way you prefer. But I mean, if you just want to give this a shot first to see if you like it or not, I would just go for the basic setup with a SEP funnel. And it's just as good. You won't get a better separation with this than you will with a SEP funnel setup. Okay. So what kind of vacuum will you need for DCVC, and what kind of silica should you use? We need a soft vacuum. So anything between 10 and 50 millibars will do the trick. And this is very easy to achieve in a synthetic organic lab. A water aspirator will do the trick. A diaphragm pump like this one will do the trick. Alternatively, you have vacuum built into your fume hood, so a house vacuum, which is also quite fine for this type of column chromatography. Under no circumstances should you use a high vacuum pump or oil pump or something like that, because the vacuum is too strong and there's a real risk of implosions, and it's completely unnecessary. And your solvent will evaporate. So I would not do that under any circumstances. Okay, so vacuum, that's easily done in all labs. Finally, the silica, and this is extremely important. The silica particle size is essential to get it right if you want to be successful with your separation. No, I'm not being paid by Merck to promote their products, but this particular product works really well. So I'm just going to show this. I'm sure there are many other brands of silica gel that will do the same trick. As long as you get the particle size right, you need 15 to 40 micrometer particle size to get a good column and good separation. If you get finer particles, your column will be eluting very slowly, so I wouldn't recommend it. It becomes too compact. If you have coarser particles, like what you would use for standard flash column chromatography, it's very hard to pack the column hard, so you get poor separation. So very important that you get the right particle size. And so now we've had a look at all the equipment you need. I think we are ready to demonstrate how to actually pack the column and get started with your purification. Okay. So now we are ready to pack the column, and before we start doing that, we have to think about safety. So obviously you're going to wear a lab coat, plastic gloves, and you'll be working in a fume hood. Also, before you start, check all the glassware you'll be using for cracks and so on, because implosion is a real danger when we are working with vacuum. So you want to have nice, clean, sturdy glassware before you start this with no cracks. Okay, I'll be packing a 4 centimeter diameter DCVC column now. It looks like that. And so what we are aiming for here is a packed column that's about 5 centimeters tall. It's not so important whether it's 4.5 or 5.5 centimeters tall, just the rough ballpark around 5. If it's significantly shorter than 5, you really lose separation power and becomes more like a filtration. If it becomes much taller than 5, 6 centimeters, it doesn't really help your purification, so you're just wasting resources and time. So try to get it around 5 centimeters. So to achieve this, you have to load a few centimeters more of loose silica. So if you load 7 centimeters of loose silica, that will end up being around 5 centimeters when you finish packing it. So now, just to help myself, I'm going to indicate on my funnel where 5 centimeters is, like that. And then I will require a Büchner flask for the actual packing of my column, and I have a rubber bung in there. So you really have to make sure that the equipment is fastly secured before you start. So you use a clamp, of course, just to avoid it falling over. So now it's nicely positioned there with the rubber bung. We can put our sintered funnel in like that, and I'm using another clamp. I'm not actually tightening it, I'm just using it to stabilize it so I don't accidentally knock it over. Finally, I need my vacuum, and here I have a 3-way tap for my vacuum, and I've already actually opened up for vacuum, which you may be able to hear or not. Believe me, it is there, as you'll see in a minute when we apply vacuum to the silica. Right, so right now there's no vacuum on the system. It's very important that when you pack, you don't apply vacuum to the system. Okay, so now we should add the silica, and I've got the Merck silica here, the 15 to 40 micrometer silica, and we're aiming for about 7 centimeters of loose silica. I think I'll just move this up so you can better see what I'm doing. So here we go. And it's really important that you do this in the fume hood. Silica is actually really bad for you, so pull down the sash while you're doing this. Now we are almost there. There we go. That's around 7 centimeters, a bit more maybe. Not that important. So now we just have to tap the surface of the sensor to get a nice level surface of the silica and to compact it a little bit. And for that you should just use something of plastic. Some people like to use a rubber tube. I've always preferred to use a plastic funnel. It really doesn't matter what you do here. Just find a solution. Something nice and soft like plastic is good because it will not break the glass. So you can see how the silica is compacting when I'm doing this. And I'm getting a nice and level surface. And already now we're probably down to less than 6 centimeters of silica. Okay, so now I'm ready to apply vacuum. So here we go. And you can see the silica being compressed even further. And now I'm going to use my presses. So I have 2 sizes here. I think I'm going to go for the bigger size for this. And this is not supposed to take a long time. If you spend more than 5 minutes packing your column, you're doing something wrong, right? It should be a fast packing. It only takes a few minutes to do this. So first you compress the column really nice and tight like this. And now we're ready to do the edges. This is very important because the edges of the column is actually where you get problems most frequently because you have channels forming. So it's very important to pack these hard. And now the little mark I made on my column is going to help me because I will be able to know when I've done 1 round of packing, right? Because I'll be turning the funnel as I go. So I'm going to twist it a bit like that and keep going. And depending on how pessimistic you are, you might do this twice. Personally, I always just do this once. The exception would be very big columns because they're a bit harder to pack tightly, and you might repeat it a few times for a very big column, but we're talking very big column. I mean, 20 centimeter diameter, that sort of thing. So there, it's packed nicely. and it's ready to go. So now we are going to put a piece of filter paper on top, simply to protect the surface when we are running the column. And of course, I have the wrong size filter paper. This is the classic problem, so you just have to cut it, or of course you can buy the right size. There we go. And now I have to check if I pack the column properly. And I simply do this by pouring a apolar solvent on, and I always use heptane. And what I want to see is when I pour a lot of heptane on, I want to see the solvent front descend horizontally down the column, right? So that's what we're looking for. So I have some heptane here. I'm just going to pour that on, and hopefully you'll see the solvent front descend nicely. It's extremely rare. In fact, I cannot remember when I last had a column that wasn't packed properly. I mean, it must be before 2000. So with a bit of experience, this is very, you can see how the solvent front is descending very nicely all over. Now we just have to suck the column dry-ish, not super dry, just until it stops dripping, and then we are ready to load our sample. So while this is happening, I'm going to show you how to load your sample. Now for this purpose, I would always recommend that you use dry loading. It's foolproof, it's a very efficient way to load your compound without having any problems. You can do wet loading if you like, but I wouldn't recommend it because there are some problems associated with that. So let's pretend our compound is in this flask. Now we want to dissolve it in a polar solvent, something that doesn't have too high a boiling point so that we can remove it again on the rotary evaporator. And I'm going to use ethyl acetate for my demo here. So I'll put a funnel in, I'll put some ethyl acetate in, there we go. And now my imaginary compound has been dissolved. And now I will add sea light, because I will absorb my compound onto, oops, sorry, that was silica gel. I will absorb my compound onto sea light. It's very important that you use the sea light and not the silica gel, because the sea light doesn't really bind the compound very strongly, so it will not compromise resolution, whereas silica gel, of course, will compromise resolution quite dramatically, because the compound will be strongly associated with silica. Right? You can add as much sea light as you like. As long as you can fit it on top of your column, it's fine, because the compound really has very low affinity for the sea light. So you have your compound dissolved with some sea light in. Now you simply put it on the rotary evaporator and concentrate it to dryness. Remember to use a splash guard, because it has a tendency to bump, so this way you will prevent putting your sea light and your compound in the entire rotary evaporator. So use a bump guard. All right, so let's pretend that I've concentrated this on the rotary evaporator. So here I have my dry sea light. I've taken it off the rotary evaporator, and I have put it on a high vacuum manifold, house vacuum, something like that, to remove trace solvents. So now it's reasonably dry and it's ready to be loaded onto my silica column. Again, I will disconnect the vacuum, so I'll let air into the system during the packing. Now I simply load my compound. And of course you can go to great lengths at trying to scrape out everything and so on. Generally this is not necessary, because you will use quite a lot of sea light to compound. So if there's a little bit of sea light left, it's a tiny amount of your compound, so it's not really that important. Right. The sea light does not have to be compacted as well as the silica gel. So just tap it a bit like this. You just need a nice firm layer of sea light on top. So no need to exaggerate this. So press it a bit with this guy, like that. You do the edges. Like that. And now you need another piece of filter paper to put on top to protect the surface. So that the surface doesn't get disrupted during columning, so you get a nice even surface. And that's basically the packing. It's very quick. You can see it doesn't take long. And we're basically ready to do our column now. Okay, so now we've packed the column and we're ready to actually run our DCVC separation. And for that purpose, I'm going to use my own preferred setup. So these custom-made receivers that we have our glass blower make for us. I'm using this small little beauty here. Now I have to mount that on my retort stand here with a clamp. So I simply attach it like this. At this stage, it's quite important that you adjust the height so it will fit to your test tube. It's rather annoying if you forget to do this because then you have to start messing around with this when you actually start running the column. So this is good. I can receive my fractions, easily get it in and out, right? I'm going to run a column using 20 milliliter fractions, so just standard test tubes in a rack. You can tell that I only have around 33 test tubes here. It's more than enough. For standard separation, a DCVC, you will be running around 25 fractions and then you're done. Otherwise, you've done something wrong, I would say. Right, I have my three-way tap here as before, and I attach it to my receiver like this. I need a rubber bung again. I put that in the top, like that. And then I have my column that I packed. Put that in the top. And then you have to sort of adjust it here to get a reasonably levels, like get the column reasonably well aligned, so the solvent will go down in a horizontal line and not at a weird angle. So something like that. And we can try to apply vacuum just to check how it looks, and it looks good. Yeah, it looks nice, like this. So we're basically ready to run the column now. The really great thing about DCVC, the reason that you get such amazing separation compared to flash column chromatography, is that you basically always do gradient elution. I mean, you could do isocratic elution, but it's simply so easy to do gradient elution that that's what you end up doing, and you get excellent separation. In fact, I would argue that you get better than CLC separation using this technique. So sometimes you will have a single spot on CLC, then you column it, and you discover that in fact that was two things. I'm going to run a column using ethyl acetate and heptane. I'm going to go from 0 to 100% ethyl acetate in heptane, and I'll be doing 5% increments. And as I said, I will be doing 20 mol fractions. So that means I will just have to add 1 milliliter more of ethyl acetate for each fraction until I hit 100%, and then I'm done. So it's a bit more convenient to have the solvents in these small beakers, so I'll do that. I use some measuring cylinders. I like these plastic ones because you tend to knock them over, and these don't break, so that's quite convenient. So I will pour the ethyl acetate into this guy, and then heptane in here. Now, interesting detail about DCVC is that the first 2 to 4 fractions are simply disappear, right? So they are absorbed on the silica. The system gets saturated with vapors and so on. So you start off with just running straight heptane through for a while. So I typically do 300% heptane fractions just to get the system equilibrated and ready to go. Vacuum is already applied. I'm just going to lower this a bit so you can better see when I add the solvent. So I'm just going to pour on the first fraction of heptane, like that. And I'm just immediately going to pour the next one on, because these two guys are just going to get absorbed. I'll prepare the next 2 fractions of heptane here. So, and when it starts coming through, and you seem like you're recovering most of your solvent, then you're ready to start the column. You can see the first bit of heptane is coming through now. It's dripping relatively slowly already, so this is about as much you will get through in a reasonable time span. So you just stop now. You let air into the system. Vacuum is still applied, but not on your reservoir. And you remove this tiny bit. So this is actually all that you get out from the first 2 fractions. And now the column is pretty much ready to go. So let's pour on another fraction and see what happens. Never throw these fractions out. You never know. If something really bad happened during your loading or packing, you might be really unlucky that your compound's in here. It's actually never happened to me, but you never know. I never throw these out until I have my compound. And now you can tell that the column is actually going very nicely. See, the tap at the bottom here is leaking a bit, so you get a bit of bubbling, but that's no problem. And you shouldn't be waiting for a long time. You don't have to wait until it stops dripping. You have to sort of move on and just keep collecting fractions. So we're just going to stop there, collect the next one. And now I'm doing my final fraction of pure heptane. And now I will start doing my ethyl acetate gradient. So I'm going to do 1 milliliter of ethyl acetate to start with, and 19 milliliters of heptane, right? And this is not a super exact science. You just have to get it about right. So no need to be super precise about this. So this first one is 19 heptane, 1 milliliter of ethyl acetate. And we're off. And the nice thing about DCVC is that while the fractions are going through, you have a bit of time to work. So I always make my fractions on the go. So I never, my solvent mixes on the go. I never make these beforehand, because you have time for it. And with a bit of practice, you will even be able to squeeze in running TLCs in this during running the column. So basically you get everything done in one go. So I think that's about right. Yep. So I hope you're getting sort of a sense of how easy this is. You're not supposed to sit here with a measuring cylinder and measure this out super accurately. I like to use the measuring cylinder for the ethyl acetate here because it makes me keep track of how far I've come in my gradient, because I can simply do basic math and calculate my way back if I all of a sudden, oh sorry, I have to remove this one first, if I'm uncertain about my progress. Right, collect that one. Let me do 2 more here. Here we go. Now a question I often get is, when is my compound going to elute? And as a very rough rule of thumb, compounds elute in the TLC, in the solvent where they would have a TLC RF value of about 0.5. So let's imagine that our compound that we're trying to isolate here had a RF value of 0.5 in 1:1 ethyl acetate heptane. Then I would expect it to elute around fraction 10 to 12, so halfway through my purification. Right, so now I'm basically putting on my last fraction. That was 100% ethyl acetate I just put on. And I'm done with my column. If I had been doing a real column and not just a demo like this, I would have been running my TLC while I was going. And I would already know which fractions I would have to combine on the rotary evaporator. Maybe I have even started doing that already. It kind of depends on how good an experience you get with this technique. But I would say that with practice and experience, provided you have your compound loaded on the C line to start with, and you just start with the equipment in front of you, it will take you 2 hours from start to finish. When I say finish, I mean your compound has been concentrated on rotary evaporator. So 2 hours from start to finish when working with 4 to 6 centimeter diameter columns. So that's really fast. You can do a lot of columns in a day. I wouldn't recommend doing more than 4. You start losing your mind around number 5. But I mean, personally, it was a very long day. I came in very early and I left extremely late. But I've done 9 columns in a day. So this is, I mean, I cannot imagine doing 9 flash columns in a day. That would just be impossible. Unless you were doing them in parallel or something like this. So this was serial. I did 9 columns in a row. Right, so that basically concludes my demonstration of dry column vacuum chromatography. I hope you found it helpful, and thanks for watching. Right, so to conclude this introduction to DCVC, I have a few practical links and references for you, and some information about the history of DCVC. So I get a lot of emails about dry column vacuum chromatography from enthusiasts, and most people tend to ascribe the technique, the invention of the technique, to me, but this is in fact not true. This is an old technique, and we basically refined it and wrote a better protocol for it. The original publication of this was by Lawrence Harwood, and the reference to his original work you can find in our paper on dry column vacuum chromatography that we published back in 2001 in Synthesis. Below me you can see a link to this paper and the reference. I'd be grateful if you could cite this reference if you have a published work where you've used DCVC, because I would like to spread the word. I think it's a very powerful and I would say environmentally very benign alternative to flash column chromatography. So I would really hope people would start using this more. Finally, if you really want some real expert advice on DCVC and have some really technical questions, I would recommend that you visit my blog, Curly Arrow. You can find the link below as well. curlyarrow.org. There's 2 blog posts on DCVC there, long ones with lots of questions and comments, tips and advice from experts and users around the world. It's very useful. And if you have your own tips and tricks and ideas, please write them there. I will respond to all comments and questions. So all that remains is for me to thank you for watching this, and good luck with your columning in the future.